So I'm Raghavendra Sai. I'm working at IIT Madras, Indian Institute of Technology Madras in southern part of India. I'm here to present work done during last 2 years. I hope I'll be able to complete in time. So chairman can stop me whenever. Actually. So here I'm dealing with plasmonic biosensors on optical fiber platform. So as you know, we have forgotten days where we used to go to a clinic to get glucose test done or pregnancy test done. But however, you see that there are a lot many more tests that actually are based on CLIA or ELISA, which have to be performed in the laboratory only, which are actually out of reach of the most of the significant number of Indians here. So our idea is to bring at least some technologies that can actually transfer some of these tests from this side to the other side. So our focus is basically to develop cost-effective but very low-cost fiber optic sensors. Why fiber optics? Mainly because you see there is always an evanescent field whenever there is a total internal reflection that takes place, and we exploit. One can actually exploit this evanescent field to detect a molecule or a particle if it can absorb light. So that means I'll show you a little later. So what happens is the fiber parameters comes into picture. They influence how well the molecule can be detected, and also in addition, the extinction coefficient, the concentration of the molecules also matter a lot. However, you see that this evanescent field on a straight fiber is not so great. That's the reason why many people have adopted a change in geometry, a modified geometry has been utilized to increase the evanescent field so that the light matter interactions can be improved. So here is an example to show how good are the evanescent wave-based U-bend probe sensors. So here you see an image of a U-bend probe. It's a plastic optical fiber of 1 mm diameter bent into a U shape having a 3 mm diameter. Bend diameter is 3 mm. So when you actually functionalize it and then dip it in gold nanoparticles, the particles keep binding, and you actually get a monolayer. In this process, you see that in fact you can actually achieve up to 4 or 5 orders of absorption. So, so these are done. These are real-time trace at 540 nanometer, absorbance at 540 nanometer. So, what we did is in the past we used those probes, gold nanoparticle probes, to realize label-free biosensors for proteins, and we could able to go down to some nanogram per ml of human. Okay, but not so great. This was the setup that was used. This is the probe that is exposed to white light, and you see pink color mainly indicating the whole nanoparticle. We also did we exploited the intrinsic properties of bacteria to realize bacteria. In fact, if you see proteins and bacteria, they do have absorption peak around 480 nanometers. Now, if you can actually send 480 nanometer light, sorry, 280 nanometers of light, UV light, and then if the bacteria comes and binds through a bioreceptor specific to a bacterium, what happens is you start seeing increase in absorbance as the more and more number of bacteria come in. So it has been demonstrated some time ago under static conditions, and under fluid dynamic conditions also we see that we can actually go down to 10 CFP per minute. So that's past. Now what we thought is we want to improve the sensitivity further, and what we did is we looked at the current technology, which is the lateral flow assay. Other technologies are POCs now. They earlier they used to use the gold nanoparticles. Now it is fluorescent beads. But the idea is you actually have a sandwich assay with label here. What we thought is, why can't we translate this onto a fiber to realize a very good? So we did that. We took a sample, we added gold nanoparticles conjugated with recognition antibodies, and we put bioreceptors on top of on the U-bend region, and we did this assay to form a sandwich assay. This is a crude but robust setup. What you see here is an LED and a photodetector from which can be quickly fed to computer. So, and this is the U-bend Silica probe, not a probe, but this is a Silica probe. Here, some surprises. We actually got some surprises. The thing is, we were able to go down to and 25 microliters was the sample. So what we did is 25 microliters of sample, and then in buffer and conjugate 25 microliters at 50, and then we dipped the probe, and we observed the absorbance, rise in absorbance as sandwich complex takes place on the surface. So to our surprise, we were able to see some changes at 1 femtogram per ml as well. You see that, you wonder why the curves are so smooth. Somehow we got one data set very smooth curve, others were on my. So I'm showing only the smooth curve. So we were able to get a clue that we are kind of able to detect 2 femtogram per ml, but we are not sure. So what we did next was we went for silver enhancement. So these catalytic properties of gold nanoparticles are exploited, and the silver gets deposited, and then what you see is further increase in the flow. So you see that at the end of 20 minutes, we washed it. That's how you see a bump here, dip here, and then silver enhances solution. Probes are exposed to silver enhances solution, and then we see an increase in absorption. And now we see that surprising, and the reviewers have asked to get back again. We are able to go down to 1 femtogram per ml of human IgG, which corresponds to 0.15 zeptomoles. And it turns out that you actually have about 100 molecules roughly in that case. And we have repeated, not by one person repeated, and 2 other people also have repeated. They are hitting this 100 femtogram per ml at least. So, well, here is one point I want to stress basically. The thing is, every dynamic range, and most of the time, clinical diagnosis have a spectrum of analytes at different concentrations. So, what you have to do, your sensor should be able to work at a concentration. So, by simply modulating, by simply actually choosing particle size, you can actually shift the dynamic range easily. So that's one of the advantages of the sensor. Well, we see that our sensors qualify for the WHO because they actually really have which only problem unlike LFA. That's one thing we have to work on. We don't know we don't get rid of that. However, you see that the silica fibers of 200 micron. So the fiber uh, it has not and however, but what we yeah in between we try to compare ourselves with one paper 15 years ago. This is how a good there is no so you could able to avoid by simply using a good combination of label and so there are problems. How would you even probes? We used to do it manually. Now we have developed an automated system to fabricate with even so. However, there are still problems there, mainly because the silica fibers are fragile, expensive. You need to clean them. You need to polish. that's difficult. So we are heading for to see an alternative in the form of a polymeric optical fiber. So what we did, we take a fiber, we bend it, we push it into a glass capillary, and then we put this glass capillary in hot air after 20 minutes. You get the fiber. We have to declare this fiber at the tip. So you still have to, but one advantage is they don't break. This is 500 microns. So these are the fibers we could able to make even 250, 500, 750, 1000 micron fibers. So we did the same assay, but however this time we wanted to look at the effect of the particle size label. If you look at 20 nanometers, you have mostly absorption. If you look at 80 nanometers, you have a lot of scattering contributing towards it. These probes are sensitive to absorption more than scattering. So we took 20, 40, 60, and 80. The excitation coefficient here is 10 power 9, 10 power 10, 10 power 11, 40 molar inverse. So when we did this study, what we found is this 60 nanometers actually giving us a better sensitivity in comparison to other ones. The 21 is understandable. The excitation coefficient is small, so that's probably the reason why we are not getting enough signal. Whereas 80, I think its interfacial effects maybe at hindrance effects that are actually reducing the field. And concentration, if we increase the concentration of the labels, we are taking the labels from here. So these labels 2x, 10x, and 20x. We did see improvement in the sensitivity, but 10x seems better because we have lower standard deviation. So we went to see whether we can actually make devices. Yes, we are able to make it. We are able to squeeze the LEDs and photodetectors into one plastic block like this. This is the real one, this is not animation. You see at the center, we have an LED, one probe for test and the probe for control. So we have two photodetectors on the other side. So this part is POC is under test. We are testing it. We don't know how good. Meanwhile, we have as an offshoot, we could able to get a crude digital fiber optic refractometer also that can be interfaced with the smart mobile. So we hope we'll be able to commercialize this technology. Maybe. Thank you very much. Thanks to the funding agency.